All right. So remember last time we started talking about polar coordinates, okay? And we're going to be doing a lot with polar coordinates over the next couple of lectures. One thing that we did is we sort of anchored the pull of the polar coordinate system to the origin of the rectangular coordinate system, remember? And then we put the polar axis was actually the positive x-axis, yes? Okay, and that enabled us to actually to locate points, not just in xy coordinates, but also r theta coordinates, where r is basically the distance from the origin and theta is the angle made by the ray emanating from the origin to the point, the angle made between that and the positive x-axis, okay? And we were able to draw this little right triangle and come up with all these relationships, like sine of theta is equal to y over r, which is the same thing as y being r sine theta, and similarly x is r cosine theta. And we have the Pythagorean identity, and we have the tangent identity that allows us to go back and forth from polar to rectangular and from rectangular to polar. Okay. Any questions on any of this? That's just kind of a brief review of where we were, but any questions on this setup before we start using it? Anything? Okay, I mean, you might be saying to yourself, excuse me, why are we doing this? Is this just some invention of some mathematician or something, you know? Well, yes and no. What this is used for is to actually describe some curves in a simpler way. For instance, what's the formula for the equation of a circle of radius 2? If I use x and y, what's the formula for a circle of radius 2 centered at the origin? How would I write that? I'll give you a hint. It's x squared plus y squared. And again, if I want a circle of radius 2, that would have to be equal to what? Yeah, 4. Okay. But that equation actually has two variables in it. And actually, if we go down to the polar coordinates, this thing is massively more simple. So this is, again, it's a set of all, what this is describing is a set of all points x and y, such that the sum of their squares is 4. That's the same thing as their distance from the origin is 2, right? Because if I take the square root of x squared plus y squared, that would be the distance of x and y from the origin. But look, if I replace x squared plus y squared with what it is in polar coordinates, that would just be r squared equaling 4, correct? Yeah? And really, when all is said and done, that's the same thing as r just being, and right, we kind of have the power to decide whether we take plus or minus 2. That's the same thing as just saying that r is what? 2. So look at this. Which of these two equations do you think is simpler to kind of think about? So all r equal 2 just means the set of all points that are at distance 2 from the origin. That's basically what that's saying, yes? Because r is essentially the distance from the origin or from the pole. Which of those two equations do you think is simpler to think about? I think r equal to 2 is simpler to think about, yes? I think r equal to 2 is basically a simpler thing to think about. So it turns out that some curves that were complicated or even looked like they weren't functions at all, in fact, weren't functions at all of x, at least, suddenly become much simpler when we convert to polar coordinates. Okay, we were doing this example last time. This was like an XY situation, right? And what we did is we said we wanted to convert to polar form. And so we used the Pythagorean identity to kind of sum the squares of x and y. So it tells us r squared is 4, which, I mean, we get to decide whether we take plus or minus 2. And we just decided to take r equal to 2 in this case, okay? And of course, what about theta? Well, I know the tangent of theta is y over x, which is negative radical 3 over 1. And I even like put a little over 2 like this, because I like to think of the sine function and the cosine function. So essentially, theta had better be an angle whose sine is negative radical 3 over 2 and whose cosine is 1/2, correct? All right, and when we did that, we realized that theta, right, an effective angle is theta equal to negative 60 degrees down in the 4th quadrant, okay? But that's not the only angle we could have used. We could have taken lots of other options as well. And so one way to express this point in polar coordinates is 2 for the radius and negative pi over 3 for the angle. But that's not the only choice. You could have also used like 5 pi over 3, right? 5 pi over 3 would have been a legitimate way to express that, because that's just 2 pi more than negative pi over 3, okay? And we talked about how we could have also been sneaky and picked a negative r value, correct? So where is this point, by the way? Well, 2 comma minus pi over 3, you know, it's like down here somewhere. So this is 1, 2, and I'm thinking of this angle as being negative pi over 3. Look, if I kind of extend this line in the backward direction, what's this angle going to be in this direction? Think about it. If going down to this other line, it's negative pi over 3. And by the way, this is the point 2 comma negative pi over 3. If going down to that line is negative pi over 3, what's the angle that goes up? Like if I were to reflect across over here into quadrant 2, what's that angle going to be? 2 pi over 3. Because after all, this angle measure and like this is 120 degrees and this 60 degrees total, that should be 180 degrees, yes? Or pi, okay? And in essence, that's what's happening. So if I wanted to go out 2 units in this direction, right? This point right here, right? That's the point 2 comma 2 pi over 3. Of course, I could express that in different ways. But if I wanted to flip down to here, all I would have to do is take negative radius. So that would be, this is also negative 2 comma 2 pi over 3. When you think about it, yes? So I can kind of go to the opposite side, flip the thing around by taking a negative radius. And that's where this point came from, yeah? The point r theta is the same as r theta plus any integer multiple of 360 degrees, yes? That'll give me the same terminal angle. And if I want to use the negative of r, I just have to shift things by 180 degrees, which is why instead of 2n pi, I have 2n plus 1 quantity times pi, okay? Any questions on that? Okay, so in the essence of what I'm saying is there are infinitely many ways to express a point in the polar coordinates, correct? I just have to choose different angles and adjust r by pluses and minuses if necessary. That's a little bit of a departure from what we've done in the rectangular coordinates. Of course, there's only one way to express a point in rectangular coordinates. Okay. All right, so what about this? Write the polar point -4, 2.3 in rectangular form. So in other words, this guy right here is r and this is theta. And what am I talking about? This is in radians. Radians, not degrees, okay? 2.3 is in radians, okay? Radians were like 3.14, which is pi. That would be 3.14 ... Pi, that's 180 degrees. So here at 2.3, 2.3 versus 3.14, 2.3 of 3.14, which is pi, would put me at 180 degrees. So 2.3 is a little bit back from there, yes? So this is a second quadrant angle, correct? Because it's a little bit more than halfway to pi, okay? So I would be in the second quadrant with this thing, right? So this is quadrant 2, okay, quadrant 2, right? Because pi, of course, is 3.14, etc. And this, right, this corresponds to 180 degrees, okay? If you wanted to think about degree measure, okay? So let's write this in rectangular form. The way that we do it is we realize x is just given by r cosine of theta. And here you have to be very careful to use which mode, like if you're happening to use a calculator? Radian, okay? So this is going to be -4 cosine of 2.3, which if you apply your calculator correctly in the right mode, you get about 2.67, okay? What about y? Well, y is r sine of theta, so same sort of calculation in radian mode. You get about negative 2.98. Now let me ask you a question. Does that disturb you a little bit? Because what quadrant is this point in? What quadrant is that point in? X is positive, y is negative. What quadrant is that? 4. But I just said that this degree measure put us in quadrant 2. But the radius was negative, right? So a negative radius, this flips us where? Flips us from quadrant 2. Oops, something's not right with this little thing. From 2, what is going on? 2 to 4. Okay, flips us from 2 to 4. So it actually makes sense that we're happening to live in quadrant 4 here. Okay, so 2.67, negative 2.98. The fact that the radius was negative flipped us across. Okay, does that kind of make sense? Hopefully. Okay, there are no other choices for rectangular coordinates. We have infinitely many choices for polar because of the angle choices, but there are no choices other than that for rectangular. Okay, hopefully that makes sense. Let's talk about converting equations between polar and rectangular form. Okay, so converting an equation from polar to rectangular form. I kind of did this already at the beginning when we converted the circle of radius 2 centered at the origin. That was a rectangular equation, and we converted it to a polar equation. It was much simpler. But let's go in the opposite direction here, from polar to rectangular. Look for pieces of the conversion equations to substitute in. Okay, so what is theta equal to pi over 4? And what that means is I want all points that have an angle theta equal to pi over 4. Let's just think about that graphically for a minute, okay? Any point that has an angle of pi over 4 associated to it, right? So that's like 45 degrees. If I want all points that have pi over 4, if I want all points that have pi over 4 as its associated angle, can't I get anything on that line that I just drew by taking various radii? Yes. So I'm going to get anything on here for sure. But where else would I get stuff? By taking negative radii, right? Because these would be positive radii. Where else would I get stuff? Yeah, I would get stuff down here by taking negative radii. Does that make sense? Okay, so you know that graphically, this is what I'm going to get. But what is that? What is that as a rectangular equation? Well, it's basically, what you can do is you can use the fact that tangent of theta is equal to y over x. Right, remember that? Tangent of theta is equal to y over x. You can plug in pi over 4. What's the tangent of pi over 4, by the way? 1, because sine and cosine are equal there, yes? Okay. So this guy is 1, which basically means that y is equal to x. All right, so theta equal to pi over 4 is equivalent to the equation y equal to x. In fact, If I give you theta equal to any angle at all, that is going to be equivalent to a straight line through which special point? The origin, yes? It's going to be a straight line through the origin. That's always true for theta equal to any particular angle. Always going to get a straight line through the origin. Okay? So line with slope 1 through the origin. Okay, as we just said. Any questions on that? So that's going from polar to rectangular. Okay, just using some of the stuff we know. Any questions? All right, moving on. Let's talk about sketching graphs of polar equations. Like we just kind of did a basic example of that just now, correct? Kind of thought about, well, theta equal pi over 4 means a set of all points that that have an angle associated with them equal to pi over 4. We got a straight line. What are some points to sketch graphs in polar form? Well, one is to plot points, right? So what you do is you basically make a table with like R's and thetas in them. Does that make sense? Okay, you say, well, if theta is this, you know, what's R, et cetera. Okay, kind of like what you did in grade school. Okay. You can also convert to rectangular form and then say, oh man, I know what that is, right? If I had no idea what theta equal to pi over 4 was, I could use the fact that tangent of theta is equal to y over x, plug in what theta is, and then convert over to rectangular form, and then I'll recognize what's happening, okay? One more thing I want to make you aware of is there are some basic forms in the book on page 721. I'll kind of show you that right now. Here are some special polar graphs. They're pretty cool. Check this out. These are called limicons. Special, they have this form right here. And depending on how A and B are related to each other, you get these different graphic type looking things. Now, I don't expect you to memorize these things. Turns out that we can, you know, easily kind of sketch these things by hand anyways. I think it's good to be at least somewhat familiar with these, but I'm not going to force you to memorize these. So look at this. This is kind of like a sideways heart. That's why it's called a cardioid. Do you see that? This is called a dimpled limicon. That's what happens when A and B are in this sort of a ratio relationship with each other. And then this thing starts to become more and more circular as the ratio A over B gets bigger than 2. Okay? Here are some rose curves right here. Okay? These arise from equations of this type, r equal to a cosine of n theta or sine of n theta. You get these cool looking things like this. Certain kinds of circles and lemniscates, okay? Like these little infinity symbols, right? They take on these forms right here. And actually, there's some pretty cool stuff that you can do in Desmos. In fact, I'm going to take one of these and kind of show you that right now. So again, remember, I know that I said Desmos is kind of a stupid machine, right? But it is pretty useful for graphing things quickly, okay? So let's look at this rose curve right here. So r equal to cosine of n theta, okay? So let's go in Desmos, okay? R equal to cosine of n theta. Okay, let's add a slider for this thing. Okay. And let's let theta go between 0 and 2 pi or something, okay? And let's go ahead. You see this? That's pretty sweet, isn't it? Yeah, I mean, do you see what's happening here? Look, and I'm even letting this thing, I think I can change this to not be so obnoxious. I want to step only by integer values. So let's go like -10 to 10 or something. Let's play this thing in the forward direction only. Let's let this thing play out, okay? I'm going to zoom in here just so you can see what's going on a little bit better, okay? It's pretty cool, right? Actually, no, I don't like that as well, to be honest with you. Let's not specify a step size. I think it's pretty cool to kind of look at that sort of thing, yes? It's a little bit more continuous looking, but that actually has in values that aren't integers, so you get some kind of crazy looking things sometimes, yes? So that's cool stuff for sure, okay? But those are some of the basic forms of these polar curves, and we'll talk about how to actually graph those things by hand pretty soon. By the way, there's a funny joke that I just want to, I mean, I can't help myself here. It basically is like, it's like this. Let me write, I'll write on here. Square root of -1. Actually, this may or may not be my joke. I'm not sure. I might have seen this on a t-shirt at one point in time or something, okay? So r equal to 1 minus sine of theta and the integral of du. Okay, so this is like a little codified message here, yes? Okay, so what is r equal to 1 minus sine of theta? Ooh, see that? That's kind of cool, right? It's a little heart shape, right? So what does this mean? What's the square root of -1? I. What's that? Yeah, so heart, and what's the integral of u? Yeah, man, I don't know. Let me see here. Now I'm annoyed because of the plus c thing. I think we need to change this to something like, oh, I don't know. Let's see. Maybe it needs to be from 0 to u of dx or something, yeah? Because what's the antiderivative of dx, of 1 dx? X, you would plug in u, you would plug in 0, and what would you get? U. That's cool. Yeah? That's a way more precise version of this. Okay. Okay, so I love you, right? So that's kind of a cool little bonus thing here. Yeah. So that is someone, guys, let me just tell you, you send a note to some lady that is written that way and they understand it. That's a keeper right there, I gotta tell you. Okay. So, all right. Back to business here. Okay. So let's actually kind of, there's another way that you can graph things. Okay, the book doesn't talk about this. This is just me kind of putting this out here because it's something that I've stumbled upon myself. Okay, what I like to do, so there's actually a fourth way, okay, that the book doesn't really talk about. What I like to do is to actually graph the thing in the r theta axis system. So I actually graph it like I would an XY graph, okay? But I put theta on the horizontal axis and r on the vertical axis. And then what I do is I translate this over to the XY system. I think about what that means for X and Y. Does that make sense? So I kind of do a translation from one to the other. What this really is, by the way, I mean, look, I promise I'm not horsing around here. What I'm really doing here is making tables. It's like I'm actually plotting points, but I'm making like a table with an infinite number of points in it. Yes, that's the essence of what's happening. So these really are kind of doing the same thing, which is why I think the book doesn't spend a lot of time on that. But what I do is I just graph the r theta thing, and then I go over and I translate that into the XY version of the graph. Does that make sense? You'll see what I mean here when we do some examples. But that's one strategy that is not articulated clearly in the book. Okay. So what about this? R equal to 6 sine of theta. Okay. I want to do this one together because I want to illustrate what I just said. Okay. So what did I say that I do? I first create, a graph in which coordinate system? Yeah, r theta. Okay, so, all right. So r equal to 6 sine of theta. Well, you know how to graph that. It's like y equal to 6 sine of x, right? Okay, so what you would do is you would say, okay, at 0, this thing is 0, correct? And then where does this thing reach its maximum? At what value? Pi over 2. Okay, so I'll put pi over 2 right here. Okay, and what is the maximum value, Maria? Yeah, so you know it goes like this. And so this maximum value is 6. And then where does it go? What happens then? Well, it goes back down to 0, correct? Yeah. And at what angle value does it go back down to 0? Isn't that pi? Okay. And then what happens? Well, at 3 pi over 2, something happens. It goes down to negative 6. Yeah? Okay. And finally, at 2 pi, this thing is back up to 0 again. Does that make sense? Now I'm going to take this thing in chunks. Okay, so now let's do the translation. Let's translate this thing. Why not? Let's translate this thing over to the XY coordinate system. Yeah? So the first thing I want to do is think about what's happening here. As the angle grows from 0 to pi over 2, so this part that I just highlighted right here, this blue part right here, as the angle grows from 0 to pi over 2, so this right here is 0 equal to or less than theta equal to or less than pi over 2, which describes which portion or which quadrant am I in if theta is between 0 and pi over 2? The first quadrant. So as the angle grows from 0 to pi over 2, the radius grows from 0 to where? 6. Okay. Okay, so I don't know. I mean, look, I'm going to just draw a bunch of dotted lines here. As this angle grows from 0 to pi over 6, the radius is growing from 0. It starts at 0 and it gets bigger, 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 bigger until it goes all the way up to 6. That's sort of counterintuitive for students at first, okay? So at pi over 2, I am out at a length of 6, okay? Okay? Does that kind of make sense? Okay, so I kind of get that sort of a looking thing. And then what happens? What happens here? Actually, you know what? I'm gonna use blue on this just so it corresponds to what we just did. Yeah, from 0 to pi over 2, that's what we get. Then what happens between negative pi over 2, between pi over 2 and pi? What's going to happen? Yeah, the thing shrinks down to 0, for crying out loud. Okay, so if the angle is between pi over 2 and pi, this thing is going to shrink back down to 0 between pi over 2 and pi, so that's going to shrink back down to 0. And I'm going to be back to where I started. Does that make sense? And then what starts happening? Yeah, so now the radius is negative. It kind of grows to negative 6. Yes, grows in quotation marks to negative 6. But that means the whole picture is going to be flipped from quadrant 3 to quadrant what? Quadrant 1. Yes. So that means it's going to be like this. Okay. So I have like that. I retrace that same portion of the curve. Yeah. And then what happens between, I'm running out of colors here. What happens between 3 pi over 2 and 2 pi? Well, I'm in the fourth quadrant, yes, but everything flips up into the second quadrant. And therefore, I'm going to trace out this portion of the curve again. You see what I mean? Okay. So this portion of the curve is traversed, right? This portion of the curve is traversed between 0 and pi over 2, but also between pi, okay, between pi and 3 pi over 2. Yeah? And this portion of the curve is traversed between pi over 2 and pi, but also between 3 pi over 2 and 2 pi. And of course, all of this is happening in this direction, okay, in this kind of counterclockwise direction. Okay, so what does that curve basically kind of look like? Looks like some kind of circle or ellipse or something like that. We're kind of unsure. Does that make sense? But it looks like some kind of circle or ellipse, basically. Does that kind of make sense? Okay, I'm translating from the r theta system to the xy system. This allows you to make sort of an infinite table all at once, which is kind of convenient. Yes, Maria. Well, because okay, so now at this point right here at pi, I'm at 0, right, Maria? All of the angles between pi and 3 pi over 2 are in this quadrant, yes? But what are all the radii? The radii are all below, or the radii are all negative, yes? So instead of being down here, where will they go to? They will go up to the first quadrant again. Does that make sense? So it will behave exactly like it did, right? This red part will behave exactly like it did on the blue part in the end, yes? Because you have this nice symmetry because the radius happens to be negative. You see it? Okay. All right. Can I erase this just so I can show you the actual tabulation, how that works as well? Okay. That really was a tabulation, by the way. It's just a graphical version of making a table, which I think is kind of nice. You could do this. You could just plug in like a bazillion points for theta. Does that make sense? And then take the various radii and then just plot those points. Okay? That's sort of annoying to do. And that's basically what I did graphically, isn't it? I just basically made a table over in the r theta plane and just translated that over into the xy plane. That's what I would have to do here anyways. Okay? And here's all those points plotted. I actually plotted all those things. Do you see that? Okay. From 0, pi over 6, pi over 4, right? So 0 is right here. Pi over 6 is this angle right here. Pi over 4 is this angle right here. Pi over 3 is this angle right here. And I'm letting the radius grow and grow and grow. Do you see that? Okay. This is pi over 6, pi over 4, pi over 3, etc. I'm just watching this thing grow. And in the end, oh man, that thing shifted. Okay. I get the exact same thing. It kind of goes over it again, which is we had this situation where we went over those points twice. Okay, so the negative radii just kind of traverse those exact same points that we had already visited from 0 to pi. Okay. And so the entire graph looks like that. So it looks like a circle, okay? Looks like a circle, which is kind of what we came up with. What about just changing to rectangular coordinates? How would we pull that off? So that is, one of the methods was to convert the polar equation to a rectangular equation, yes? Could have plotted points, could have made the r theta graph and translated to an xy graph. But what if, is there a way we could change this to rectangular coordinates? And the answer is yes. What you do is you start with this and you say, well, I don't know what 6 sine theta is, but I know what 6 r sine theta is because I know what r sine theta is. What's r sine theta? Y. What's r squared? X squared plus y squared. Yeah. So once I have this, I actually know what's going on because r squared is x squared plus y squared. R sine theta is just y. And the r and theta are completely obliterated. Yes. And now I simply have an equation in x and y. And what do you suppose I'm going to have to do with this guy? Thinking back to what we did with all the conic section stuff. What do you think we're gonna have to do with this to figure out what this is? Complete the square. So this is completing the square, right? Basically what you have to do is you have to add 9 to both sides, and you get x squared plus quantity y minus 3 squared equals 9. What is this? What kind of a conic section is this? The circle of radius 3, centered where? Yeah, so it's a circle of radius 3 centered at 0, 3. Okay, that's cool. There it is. Yeah, does that make sense? So that's another thing you could do. You could convert to rectangular form and then just think our way out of it. Okay, so we get that. Any questions on that? I think that's pretty cool. All right. You could recognize the form of the graph basically from page 721 in the text. I don't know. I'm not really someone that likes to memorize a bunch of stuff. Honestly, I don't even have those things memorized. I just every time do that r theta thing and translate to x, y. That's what I do personally. Does that make sense? Or if pinched, I will actually go and work in like, you know, if in a pinch, I'll go and do something in Desmos or some other technology, for instance, okay? Here we actually have Maple. Some of you engineering people will use Maple or MATLAB. The math people will use probably Maple more than they would use MATLAB. That's another technology. I actually put some code in here to do these sorts of things at the end of the slide presentation. So again, a circle tangent to the polar axis, diameter corresponds to coefficient of sine theta. That's what you would get if you went and looked at that page in the text I talked about, or that I showed you earlier. There it is. You will need to be able to sketch them quickly by hand, and usually you can do it, but by quickly I just mean maybe make an r theta thing and then translate that to x, y. But it better not take you like 45 minutes to graph one of these things. Does that make sense? So you just need to be able to do it relatively quickly. Okay. Circles, cardioids, and rose curves, you should be able to go boom and just kind of handle it pretty quick. Yeah. Here's some, I just put this in here for your amusement. You can, you know, any Cedarville machine has access to Maple. And here's the code for plotting things, where R of t is whatever the, you know, whatever the specific polar equation happens to be. Yeah, you can kind of plot that thing. Also in your calculator, do you realize that there's like a pole mode, POL, that will give you sort of a polar equation form for things. Polar coordinates are so prominent that they get their own special mode in the calculator, even though polar coordinates are technically just a particular kind of parametrization, yes? But it comes up so often that it gets its own mode in the calculator. Okay, we'll spend some time tomorrow doing some more graphical things, but that's the gist of what I wanted to get through today. I think that's it. I am done. We're done a little bit early.